Thank you very much, Katara. Okay, so let's get started here. You know, people talk about, is it the end of Moore's Law? And I still love this quote from Alan Kay that said, I predict Moore's Law will never end, so I'll only be wrong once. But in fact, we are starting to see the headwinds. And in fact, Moore's Law is not ending, and yet paradoxically, it's not delivering anymore the kind of performance gains that we've been used to. And it's not because of our ability, our inability to shrink transistors. In fact, we are continuing to shrink transistors each generation. The problem isn't the transistors, it's the wires. So with the transistor, you know, the traditional equation here is, you know, voltage squared times the clock frequency times the capacitance. When you shrink that transistor, the capacitance continues to go down each generation. The transistors are getting more efficient, but long time ago, like we're talking back in 2005 or so, the amount of energy going into the wires has surpassed that going to the transistors, and it gets worse every single generation. And that's because the power consumed by a wire is the frequency times the length divided by the cross-section area. And so that means wires do not improve in their energy efficiency as you shrink them, whereas transistors still do. But the transistors hardly matter anymore. And that's the future of computing, and that's why people say Moore's Law is ending. Well, if it's shrinking the transistor is what's ending, no, that's continuing. But our ability to extract more energy efficiency in each generation is challenged by that. This is the diagram we put into the DARPA Exascale report. So there was a hardware report. I was involved in the software report, but this again was to inform our algorithm developers that you have to worry about data movement distance more now than the computational aspects. And that means you might want to reformulate algorithm order of complexity based on data movement rather than flops consumed. And there's another crisis going on, and this is for the photonics people, that the total amount of power necessary to escape the package, the chip, is actually, the power for the off-chip I.O. is matching that of the power consumed by the computation within the chip. And that's yet another crisis that's data movement related. This is another kind of way to look at what's, this is from Shekhar Borkar. We did a report a few years back for the Office of Science Technology Policy, and you know, for the terascale era, we get 32x energy efficiency improvement from the transistor and 32x from increased parallelism. By the time we got to the petascale generation, it was 128x versus 8x. And here we are in the exascale generation, and you can see from Peter Kogi, we just read this straight out of Peter Kogi's paper with Bill Dowley, 670x from parallelism. And we're talking explicit data parallelism here too, and only 1.5x from the transistors. And this is the paper that I did with Shekhar for the Optical Society, which is this is the amount of energy that goes to your on-die energy, moving data around in tiny little wires, and this is how much is going to the transistors themselves. Compute isn't the issue. It's data movement, and copper is about as good of a conductor you're going to get at room temperature today. So this is an engineering challenge for us who do computer architecture. And this is also traveling into the AI market. So this is from our friends at AMD. The ChatGPT and the Meta AI cluster that drives that is requires as much energy as Ireland and Germany combined. I talked to the CEO of the Dominion Power, which serves power in the East Coast. They now have more generation capacity online for the data centers in the Eastern Seaboard than they do for houses and other consumers. And you see this diagram is clearly hand-drawn, but I think that the point is very clear, which is that we're getting to a market dynamics limit for energy consumption going to computing. Of course, the hyperscalers are driving this because of NVIDIAnomics. They make $5 for every dollar invested in a GPU, but despite that, it affects us in HPC too. And this is what it looks like for us in the HPC space. So this is The LINPACK benchmark, so this is your performance of systems as measured by the LINPACK benchmark. We had a steady 1000x every 11 years. And our complaint about the LINPACK benchmark is it's irrelevant because it's too easy to deliver flops. And yet, despite the fact it's a too easy benchmark, we can't even deliver the flops because we consume so much energy in all the other aspects of the system related to data movement. So even with LINPACK, we're failing if we continue with business as usual. And it's not an acceptable future. And you know, if you build a bigger system, so we go from Exascale to whatever the heck next to scale is, scale alone is just power and capital. And the hyperscalers can do power and capital because they're like able to afford to bring nuclear power plants that melted down in the 1980s back online. We're not going to be doing that, I hope. So now let's look at the scientific challenges, though, that motivate us to get to the next level of performance for systems. So this is an example with cloud resolving climate models. We know that our inability to directly resolve clouds and mountain peaks is one of the biggest sources of error in our existing Earth systems models. In fact, we're unable to, with our contemporary codes, reproduce superstorms like Sandy at any epoch. And so that's what's motivated these hero runs like this. So our state-of-the-art for 400-year models is this 25-kilometer. There was a really landmark 3.5-kilometer scale model that ran on Frontier. It achieved 1.5 simulated years per day of performance, which is fantastic. It smashed all previous records. It's an amazing accomplishment that the E3SM team did. And so that means at this rate, an ensemble calculation would take a mere 20 years of dedicated time on Frontier to complete. Doesn't seem to make sense. So that's make it very difficult to answer important policy questions that we need to have answered by 2055. Depending on which administration is in then. So if we also look at projecting to 2055 just at the rate of performance, both algorithmic and hardware, because in fact, E3SM has actually been improving in the algorithmic side almost as much as they have in the hardware side as they go forward. And so if you project that out, we're also hitting 2055 before we can get the answer fast enough to be actionable for policy. So that's not an acceptable future when there's important scientific imperatives that have global societal consequences. We got together with the folks from NVIDIA and AMD and a bunch of the climate modelers and worked out all the details of what's required to achieve this. And the interesting thing is that to get that 1.5 simulated years per day of performance, their memory footprint is only 120 megabytes per chip. On the system, on the Exascale system, which means they could run entirely out of the SRAM potentially, except for other inefficiencies, but we'll get back into that later. There's not, memory bandwidth isn't necessarily the limiting factor here. Another example, high performance density functional theory. Last measured on NERSC, it was about 1/3 of the workload, and almost all of that, 80 to 90% of that was VASP. And it's been a fairly standard, settled algorithm for many years. There's not a whole lot of new innovations happening, and it allows you to predict the performance of materials from first principles before you've even synthesized them. So it's a real workhorse for BES community. It's a very, the central step here, though, is fairly straightforward. It's 3D FFTs, fairly small ones, but a lot of them, followed by dense linear algebra. Big opportunity for performance gains there, and localized basis sets and plane wave basis sets enable us to use communication avoiding algorithms to implement this. So if you get an excellent accelerator, you won't be limited by the inter-node communication. So let's talk then about what are we going to do about this. I want to talk about a new project in Oscar's competitive portfolios in computer science research. And our project is the algorithm-driven co-design of specialized architectures for energy-efficient HPC. In the bigger context here, DOE is making major investments in the CHIPS, which is NIST-led, in new materials and devices. But we know that it's about 20 years from lab to fab to get those new devices into volume production. So given that we don't have any obvious candidates for CMOS replacement today, we're kind of already 10 years too late to have an impact on the 2030 system. So that's why I'm very interested in this meso, this intermediate scale of 10 years out, which is more efficient architectures and packaging. And in fact, there was a report from the National Academy of Sciences where their bottom line was that we got to expand and create where necessary these integrated teams that aren't just a bunch of hardware designers, but they're actually the algorithmic and data access motifs, figuring out alternative formulations of the math in order to work together using a first principles approach to develop the next generation of accelerators. And this is the recommendation that Kathy and Dan Reed had for the future of computing in DOE, and we're taking this to heart as a deeply embedding the applications and algorithms in together with the folks that are designing the next generation of hardware. Another aspect of this, though, is that addressing cost is crucial. We know that we can't engineer a full custom machine. We did that back in the 90s. We stopped doing that. It was Attack of the Killer Micros. But there are alternative methods of integrating these kinds of specializations that are cost-effective and affordable. The rest of the industry is moving this way. I'm bringing to the table that we need to consider this too as a way to have our cake and eat it too. Get those specializations that are crucial for HPC inserted into a commercial platform without bearing the entire platform cost, which we know we cannot afford. And so we've got establishing collaborations with industry and the hyperscale architects from the get-go to exploit those opportunities. So this is the team. You can see that there are almost as many applied mathematicians on this team as there are hardware architects. We've got folks from Argonne, CAS, Berkeley, University of Houston Clear Lake, and so we have these overlaps too of people like Damien who cross over between the applied math and the computer compiler systems, and folks that also are crossovers from applied math into computer architecture like Tom and CAS. So you've seen, a lot of people in this room have seen it before, but just in case, specialization, this is nature's way of extracting more performance from a resource-limited environment. It's also a computer architect's go-to. GPUs started as specialized, and we found a way to generalize them in a way that maintained their performance advantage over a general-purpose CPU, while at the same time being more tailored to expand into science applications. So we had the powerful general purpose CPUs. When we entered the post-Dennard scaling era, the creatures react by having a lot of smaller little copies that are more efficient. That's what an Intel Knights Landing was, and to a certain extent GPUs. And we're entering this era where you got post-Moore scarcity, and the critters got to go after different food sources, and they evolve specialized beaks. And this is exactly what the rest of industry, Apple, Google, Amazon, Microsoft is doing, and in a lot of other elements of industry. And we need to learn from what the rest of industry has done. That's the lesson of Attack of the Killer Micros. Look at what the larger industry is doing, figure out what lessons you can learn and reapply to our space, because we can't own it all. And so as an example, as a proof of concept, we developed a generator, to be more correct, Xiaokun and Tom and Mario developed a generalized multidimensional mixed radix FFT accelerator. We showed that these high productivity hardware design languages like Chisel enabled us to do it with only a handful of code. Only 3 different codelets necessary to synthesize this. So it's not like Verilog where it's a million lines of Verilog code to design hardware. You can do an entire RISC-V processor with only 3,000 lines of code. So the accomplishment is, despite this being generalized so that you can do all the stuff that FFTW can do, when we synthesize in 16 nanometer TSMC FinFET, this is basically 50 times more dense in terms of, in comparison to a state-of-the-art NVIDIA H100. It's also 50 times more energy efficient per floating point operation that it's capable of executing. So 50 times less space, 50 times more energy efficiency, despite being a really obsolete technology node. And we just got our 7 nanometer PDK, so we'll try this again and see how much we can do to beat up on a contemporary machine. But the goal here is to generalize this approach, though, to generators that can attack primitives that cover a broad spectrum of algorithms that impact DOE applications more broadly. And so we do have, you know, some targets, some example applications that we're using to motivate our work, and be able to have some specific problems that we know, looking at roadmaps, will not be addressed by existing roadmaps going into the future. And find out and diagnose, understand what the technological limits are and what could be done with hardware to change the game. Our methodology is, you know, our baseline is really to do performance breakdown, diagnosis, analysis. I know Jens does a lot of this at Recon. The next up, though, is the roofline model, and this is to establish the theoretical and physics-limited peak. And something I'm going to talk about, if I get to it later on in this presentation, running out of time quick, is that once you do the roofline, you establish physical limits. You can't violate the speed of light. This is where our friends from the applied math community start to get in and do their work, which is to change the roofline. There are many different ways to formulate Poisson's equation, and some of those formulations enable us to move those rooflines in ways that enable us to break out of the current way that we do things, and that's where the hardware and software co-design comes in. With the algorithmic reformulation, it has you reconsider the limits of the software. Next is use software simulation, you know, ModSim like Gem5 and SST. But we also have developed a specialized capability over the past several years for FPGA, not just emulation with FPGAs, but we've actually got tools that have been developed between us and Berkeley campus to actually make these FPGA simulators that can run fast enough that you can boot Linux, so 250, 300 megahertz, and run applications at scale. On the FPGA clusters in order to do the algorithm part of the evaluation, rather than the current with software, you know, you get 2 nanoseconds per day kind of simulation rates. So this is a game changer for us. And then finally, we do RTL finalization and synthesis, so you can see what the real impact is in terms of power and area. Some of the tools that we apply to this, we have Chisel, of course, as a high productivity hardware prototyping language. It's not high-level synthesis. It's still structural like Verilog is, but a whole lot more efficient because it uses modern language features like inheritance, polymorphic types, stuff like that, so you can have a very small amount of code, have a very big impact in terms of being able to explore the design space. We have Gemini and Chipyard, full-stack SoC generators with many different RISC-V cores to choose from. We have Mosaic and FireSim, which is a scalable FPGA emulation and simulation environment that enables us to fit hundreds of RISC-V cores and accelerators onto each FPGA. So with a cluster of FPGAs, we can simulate a rack and do it cycle accurate and boot Linux. And then the last one is MetaLift, is a framework for building compilers for domain-specific languages. This is a way for us to actually attack the problem of going from manually doing all this, even though Chisel's higher productivity, still manual. MetaLift is an approach that enables us to do semantic analysis so that we can automate these tasks in the future and go straight from an algorithmic spec to performant hardware. Again, this is following industry trends. This is from Leeserson and Thomas, where we went from a transistor focus where you could separate your applied mathematicians from your hardware designers. You shrink the transistor, it all gets better. Now we're moving to a systems focus where shrinking the transistor isn't getting you what it used to, so you have to consider the co-design of hardware, software, but the algorithms. And that's been the missing. When you talk about hardware, software co-design, Algorithms isn't software, algorithms is math. And this is the missing piece that we need to bring into the equation to really have tackle this challenge of hardware-software co-design. Our friends from the hyperscale are also looking at similar fragmentation, similar systems focus, and you're seeing a lot of specialized hardware coming out of the hyperscale space. The key feature that we're leveraging here is that they are making major use of chiplet type integration technology in order to lower the cost so they're affordable, so the mass costs aren't killing them. Yes, they have a lot of money, but they don't like to waste it. They like to make money, not blow it. And so we can learn from that. We can also learn this is basically heterogeneous integration roadmap. This is a cross-industry effort where you have Intel, IBM, TSMC, ASME, all working together to create a pre-competitive roadmap that shows what we could do together to create these heterogeneous chiplets packages. So let me just dive quickly into, so what the heck is a chiplet? But there's a lot of industry focus on this because industry folks were like, no way we're going to 2 nanometer with the mass cost. It's like crazy. So chiplets enable us to co-integrate reusable functional blocks that might be implemented in obsolete technologies, like memory controllers don't need to be leading edge. And this enables more participation in leading edge fab processes to get more energy efficiency without having to own the entire chip. So what's a chiplet? It's actually been around for several decades now. In fact, the FPGA people did it first, but AMD has brought it into the mainstream, and after AMD, Intel, for scalable manufacturing. It's really that we couldn't afford to increase the SerDes rate. There's no Moore's law for pins in a package. They've been stuck at like 0.8 millimeter bump pitch for decades now. And but what you can do is use an obsolete lithography process to engineer lots of little solder microbumps, now copper micropillars, and now you're benefiting from parallelism. Just like we do with scalable HPC, we're benefiting from parallelism of these pins. So instead of a few pins operating at ridiculous SerDes rates, which burns tons and tons of power, you can co-integrate things, have massive bandwidth between them, but by going lower SerDes, more energy efficient, and also you get this benefit of modularity, and the last benefit you get is higher yields. When you do a reticle limited design, the likelihood that you're going to have a serious defect that kills the whole chip goes way, way up. Doing known good die with these smaller chiplets and co-integrating them after you've tested them, way higher yields, way lower cost. So I don't want to imply that these 2D planar things is the only thing. This is what's mainstream right now with AMD and Intel, but there's lots of different ways to use chiplets and co-integration. But this is an old DARPA slide from 15 years ago. They saw this as a thing 15 years ago, but now it's actually mainstream, and you actually have backing of all the major fabs and packaging houses for it, which is you can have access to your commercial IP, which is the expensive part, is having all the compilers and all the support for the platform that you can buy off the shelf from ARM or whoever, and you can co-integrate your specialized block with that commercial IP that also has the software support, which is crucial, and have just massive data movement between those elements. And so this is what's being offered to us. Actually, it's being offered to the hyperscalers, but the hyperscalers and our suppliers here are saying, hey, you guys can jump on this too. So let's do the experiment and see what we could gain by jumping on. This is AMD has already talked about offering a spot. Instead of putting a GPU on there, you could pop one off and instead integrate third-party IP. Again, focused on the hyperscalers, but it's something that we in the HPC community could also get access to and talk to AMD about it. Same with Intel, modular platform where third parties, it's oriented around having third parties being able to integrate into their package, and in so doing into their platform. And then ARM more recently opened up the door to custom chips for HPC and AI. And we also have Patricia and George are leading an effort with the Open Compute Project, which is a front end for the hyperscalers for modularity with chiplets for both HPC and AI, where we're getting all the hyperscalers to talk with each other and our suppliers about what kinds of standardizations can we do to make this accessible to the HPC community, but also the hyperscalers. So, you know, we're right here, right now we're in a semi-custom multi-vendor chiplet platform. This is basically where we're at today is AMD is just starting to open up its platform so that if you give all the IP over to them, they can co-integrate it because they've already got all that stuff figured out. But, you know, the place where the Open Compute Global Summit wants to go and where ARM wants to go is an open chiplet marketplace where you can co-integrate IP that comes from lots of different potential players. That's how the current licensable IP market with ARM works today. This is basically, instead of having to fab a separate chip each time you want to integrate some new piece of IP, you can actually co-integrate them as chiplets, and then you don't need a new mask, and also you get to take advantage again of your commercial platform, which that is the expensive part, is it's not just the chip. In fact, when you make a chiplet, it's much smaller, so it's much more cost effective. It's everybody who makes the board designs for these suppliers, everybody who does the packaging houses, the TSMC relationship, and all the software, even the cooling solutions. That's the really expensive part. Chips are expensive, but the other stuff's even more expensive. All right, so we have developed, to get us into this, an open platform called Mosaic, which eliminates the need to have drivers to co-integrate a bunch of accelerators together on a common platform. But it also, it normalizes the memory mapping and the way that these things communicate. But it also gets rid of the offload model for inter-accelerator communication. Now they can be peers. And so if you drop something like your accelerator into this little, what do you call it, sandbox that we've developed, now you can have a bunch of RISC-V cores, but you could replace some of them with unstructured data processor from Argonne or SOTA synthesizer for PNNL. And they can all communicate with each other without having to have a driver. They just speak through PGAS primitives. We have hardware message queue support, one-sided messaging support, again, in hardware, so you don't have to invoke MPI. And you get single cycle kickoff of very tiny messages, so that it's very, very efficient interprocessor communication. And working together with AMD, we're looking at a way where we can experiment with stuff in our FPGA simulation platform, but we're working to normalize this interface here so that instead of our open source IP over here to create this uniform memory fabric, we duplicate all of the services that AMD has through its HIP. And they can drop in their IP here, and suddenly your design that you dropped in over here can be dropped in seamlessly into the Infinity Fabric in the commercial platform. So once we prove things out using the simulation platform, if it really works for us, maybe it won't work, then you have a pathway to integration with a commercial product. And that's how we're trying to keep it affordable. So, you know, the impact is to try to come up with a growth trajectory that enables successive generations of DOE supercomputers to deliver performance scaling in dimensions other than just making a bigger machine. This is proving, you know, controversial hypothesis that we can have hardware specializations that deliver the kinds of performance enhancements like extreme strong scaling or things that are genomic analysis oriented where you have 2-bit, you know, words in there, and be able to co-integrate it with a commercial platform. We've started early with AMD, NVIDIA, the modular AI and HPC part of the Open Compute Project, and we have Project 38, which is a DoD project. All of these are partners in this process. We can't do it alone, and we're continuing to move forward. I'm going to skip through this and just get to another interesting observation that I think might be interesting. Software and algorithmic challenges for chiplets. So just because we made a specialized chiplet doesn't mean you just drop it in and it works turnkey for your workload. That's actually not what's going to happen. And so, you know, we have, this is a picture from people who are doing AI, but in fact it's informative about, you know, old school parallelism the way that we've been doing it too. So we have straight up data parallelism, and then you also have model parallelism. So tensor parallelism is more or less like the domain decomposition we do to get scalability. I don't know of many people in the HPC space that try to do pipeline parallel. I know that Paul Woodward does this, but I don't know many other people that attempt it because it's hard. But as you look at large language models and the insatiable need to continue to scale training, we're starting to see more different dimensions of parallelism than strictly data parallel to emerge. And in fact, many more than just the three depicted here. There's about 7 different classes of parallelism you could point to that are already emerging in the AI space. And the key is that, you know, you saw from Shekar's diagram, we've almost completely tapped out data parallel as a way to go, and we need to look at other dimensions of parallelism, and that's where our applied math friends can help us. This is just an illustration of, you know, we're going from languages, we're deeply baked in this notion of von Neumann computing where, you know, even if it's parallel computing, I do this, followed by this, followed by this, followed by this. Even if it's CUDA, that's kind of the way that you think about things. When we're doing these FPGAs or some of these emerging devices, or if you want to do a full custom circuit design, we're really talking about more of a data flow expression, and it doesn't, there's not like a really good, a fine transformation from this way of expressing things to this way of expressing things. And to illustrate the point further, it also breaks encapsulation. So we're used to having hand-tuned high-performance libraries like BLAS and FFTW, and you invoke them sequentially. And each time you invoke them, you're doing a full round trip between memory and the compute and back. When you look at really performant, specialized hardware, it actually is more data flow where you get to chunk things up and reuse stuff while it's still on chip. This transformation, well, first thing is it breaks the encapsulation that subroutine calls provide us, but it also is a very difficult transformation to implement automatically. It's very fraught. And so, you know, we did a preliminary thing with density functional theory, reformulating it from a standard eigenvalue problem with the central step into a data flow kind of circuit reformulation. And it was very non-trivial and requires a lot of external cycles of optimization in order that we're not used to with conventional compiler technology. We also had a way to map it onto our specialized accelerator environment, the Mosaic. The key finding here, though, and this is a discussion I want to have some more with Jens, is that if we don't reformulate in this way with the specialized hardware, this tiny little yellow part is the compute part if we have a highly performant accelerator. The blue here is the part that is data movement. And as long as we continue to invoke and package things as these hardware accelerator, libraries in the conventional sense, you'll be completely pegged by data movement cost, completely. And there's no way out of it because it violates physics if you go out of it. Now, if we reformulate it into this more generalized data flow form, and that required not just a transformation, like a loop transformation, this required a reformulation of the algorithm at a fundamental level. Now we can get to the point where as we merge these stages, we can get back into being limited by compute and not by data movement. And this was one of the core findings that we had from our preliminary work. You can actually even write a compiler Python script that does this for conventional CPUs, and we get a 10x improvement in performance on average. But it can also give us a huge boost in terms of performance of accelerator platforms. And it also tells us that the offload model is a completely unproductive way to exploit heterogeneous acceleration. Not in the cards. And so that was something, an insight that the applied mathematicians gave us, was that we have to go to a peer model for acceleration or this is not going to work. So that's it. I'm going to stop here. You know, conventional wisdom is at the era of the universal computer. Scale was the correct answer to deliver more to our customers. And the new wisdom is this new era, scale alone isn't a viable way to continue. It's just more cost and power. And the hyperscalers got a lot more cost and power than us. So let me take some questions, since it sounds like I'm at the end of my time.
Okay, so thank you
Thanks.
very much. Yeah.